Hello everyone, my name is Xiaoyi Shi. I'm a software engineer from Tencent. Today I'm going to share our journey of migrating a gigantic iOS app to Bazel. The app we migrated is QQ, which is a beloved messaging app in China. Compared to other instant message apps, it comes with a full pack of entertainment features like games, short videos, and etc. The earlier stats show that QQ has over 700 million active users per month. So why do we need this migration? First, because of size. The first version of QQ for iOS was released in 2008. Over the last decade, it has over 8 million lines of first-party code. To make all cool features possible, QQ uses over 300 second and third-party dependencies. Right now, over 200 engineers are working on the project. To make cooperation possible, we have put lots of effort in writing docs and improving workflows. However, navigating through a large code base like this is still challenging, not to mention building and testing. Second, because of speed. As the complexity grows, the app becomes slower and slower to build and test. Even with a lot of optimizations, a clean build on CI will take more than an hour, and an incremental build will take more than 20 minutes. Because of this, engineers prefer submitting large chunks of code to minimize the overhead, which in turn makes quality assurance another challenge. Therefore, we set an ambitious goal for this migration, which is to make the builds 30% faster on CI. And if things worked out smoothly, we want to improve the build and test experience on workstations as well, and eventually improve the performance of the team. Before we start, I'd love to go through some of the attempts we tried earlier. This should help you decide which is the best path forward. The first one is a hack over the existing Xcode build system. It is the most transparent to engineers. The fundamental idea is to override the default CC and LD tools with a wrapper and provide centralized caching ability in that. So when the tools are invoked with the same arguments, we can return the cached artifacts instead. However, as there's no way to guarantee that everyone uses the same version of the tool, and some transitive dependencies may escape from the dependency analysis. As a result, the cache can be easily polluted and cause incorrect builds. The second one is through pre-built modules. We ask the feature teams to break the product into smaller chunks and release them as frameworks. By doing this, we only need to build once, and other teams can download frameworks without waiting for the build. However, this solution turned out to be problematic as well. With Xcode, there's no way to create a strong module boundary. Even with modular design in mind, people can easily use another module's code by mistake. So modules are still tightly coupled with each other, which makes releasing them a huge problem. Most importantly, debugging pre-built binaries is not fun at all. After seeing previous successful migrations, we decided to give Bazel a try. Bazel is known for being fast and correct through hermetic and reproducible builds, so it's guaranteed that we can get the best part of the previous attempts without those pitfalls. After poking around with some small modules in QQ, we realized that migration won't be easy. There are three major blockers. The first one, Xcode encourages base name only imports and supports recursive search passes. To avoid having performance issues when having too many search passes, Xcode actually extended CLang to support a header map for lookup. However, as Bazel is not bound to CLang, there's no special optimizations for this, which makes the header lookup extremely slow. Second, as I've mentioned earlier, we have switched to a module design. So each module manages its own set of build settings. As Xcode doesn't support config inheritance across the project, there are a lot of inconsistency in those configs and makes writing code build files a nightmare. Last, because we have hundreds of Cocoa Pods dependencies, and not all of them behave. To those who are unfamiliar with Cocoa Pods, it is a dependency management system written in Ruby, and it uses Ruby scripts as configs. Because of this, people can do arbitrary things in it, and we have seen cases where people run downloaded scripts while declaring a dependency. So making them work in Bazel is almost impossible. With these challenges in place, asking the feature teams to perform the migration will only scare them away. Instead, we decide to automate the process by generating the build files and run Bazel as a shadow build system, so that we will be able to collect performance data without changing a thing, and let the numbers speak for themselves. In a nutshell, we want our users to forget about the build files and let the tool generate them. How do we generate a build file? Let's take a look at an example library target. The most important part is the source and depth, which defines the library and the relation between them. These configs are considered as the foundation of a target. The other part is the build settings, which controls how the compiler works, like the macros and toggles the certain compiler features. To summarize, as long as we can figure those out, we can generate a build file. QQ is written with Objective-C. Let's take a look how OC is built. Here's a piece of OC code, which implements an example class, which has a sayHello method to log a greeting message. This file has three imports: the foundation framework in the angled brackets for logging, the BZC bundle.h in quotes for getting the year of the BazelCon, and the last one, the example.h for the class definition. It seems quite straightforward, but can you tell which BZC bundle.h it is importing? To answer this, we need to look at the build script. Like all C family languages, build flags plays a critical role. They determine how the source file is interpreted. The -i flag sets a header search path, which in turn determines the actual dependencies of a source file. Other CLON flags are the build settings. Interestingly enough, we need to check the LD command to figure out what source files are in the library. As you can see, the library has only one object file in it, and the file generating that object file is the source file for the library. To sum up, Objective-C is now designed for automation. It has no convention at all, and the configs are everywhere, which makes us wonder, is automation possible? Of course, it is possible. Let's make it work. The first step is to define the problem, which is resolving ambiguous imports. When the compiler resolves an import, there are three factors in play. First, the import statements, then the content of the codebase, and last, the build settings. As shown on the slide, by changing the order of the header search passes will result in totally different build results. This is because when the imports are ambiguous, the compiler will try each of the header search paths to see if there's a header file exists underneath that, and use the first encounter as the search result. The naive solution is to capture all three and resolve imports accordingly. But this is way too error-prone and slow. The intuition is that when someone writes the code, they have a clear idea of what file is needed. But as only partial information is kept in the source file, it has a tendency to deteriorate. So as long as we can preserve this information, we will be able to tell exact file it is importing. To recover this information, our approach is to use step files generated during the Xcode build, which includes all the transitive dependencies of a target. This works because if our users are happy about the build result, the header resolution must be correct. We create a tool to expand imports to the full path relative to the workspace root. so that we can tell the dependencies from the source files alone. The second problem is to figure out the source and build settings. As I've mentioned earlier, this information is hidden in the final build command, and those commands are generated with Xcode magic. After realizing we can't counter the Xcode spell, we settled with the approach of finding the source files for a target from the Xcode project files, and using Xcode build, which is part of the Xcode toolchain, to figure out build settings inheritance, and eventually use Xcode buildsettings.com to translate those build settings to CLang and LD flags. Now we have all the necessary bits to generating a build file. We decide to extend Gazelle for Objective-C. Gazelle is a build file generator originally designed for Golang, but can be extended to support arbitrary languages. As you can see, it's a simplified root build file. It has a Gazelle target, and one can use Bazel run Gazelle to generate build files for the entire workspace. As we have extended Gazelle to take Objective-C related directives. So when running it, it will know which Xcode config file to use. Now all we need is to make sure that people run Gazelle after writing the code. Instead of changing the workflow, we create a small script to run Gazelle from git commit hook. Also, to make it run fast enough, we should pre-build Gazelle in the repository and tune it to perform incremental updates based on the change. With those efforts, no one will ever need to create or update a build file manually. So far, we have managed to introduce Bazel without changing the workflow. However, to finish the migration, we need to use it. Given the size of our app, we need to do this gradually, so that all the changes are well tested before hitting the market. The strategy is to leave Xcode alone, then run Bazel as a shadow, and finally take over. This rules out tools like Tulsi, as it will jump to the final step and forces everyone to accept Bazel as the source of the truth. The idea is simple. Don't touch the existing Xcode targets, and create a shadow one to build the same source file with the same config in Bazel. Then combining the two. We call this hybrid build. The workflow for the engineers stays the same, and because the build files are automatically generated, so shadow targets will pick up changes in the original targets without human intervention. After creating those shadow targets, we can gradually change the dependencies of a shadow target to use other shadow targets. This gives us an independent shadow build graph to work with. Moreover, we can run benchmarks against both build graphs in parallel. The last piece of the puzzle is Cocoa pods dependencies. We have way too many pods in our app. We'd love to use some automation tool to Bazelize them. Unfortunately, as I've said before, not all our pods behave, so none of the existing tools works out of the box. As Bazel is already capable of managing external dependencies, so instead of improving tools to support our weird cases, we want to replace CocoaPods with Bazel someday. We end up with a semi-automation solution. Let our tool generate a basic skeleton for each pod and manually tweak the build files to work. The initial performance was not impressive, so we took the path for optimization. After analyzing all the profiling results, the problem boils down to one thing: dependencies. The short answer is that the fewer dependencies, the better build performance. In practice, you can use tools like include what you use to reduce the number of imports in the source file, which will then reduce the number of dependencies. Also, eliminating precompiled headers will help a lot, as they will become dependency hotspots and slow everything down. And finally, use fine-grained libraries. The glob unlinked is easy to maintain, but it's bad for build performance. First, it will put too many files in the Darwin sandbox and makes it even slower to start. Second, it reduces the cache hit rate, as unnecessary files are considered as action input. Therefore, it's more preferable to create libraries with fewer source files. To illustrate this, here are two identical build graphs. The left-hand one uses coarse-grained libraries, and the right-hand one breaks those libraries to fine-grained ones. The first one will introduce many unnecessary files to the action sandbox, say O A123, B123, and C123, while the latter only includes exact files needed for the action in that sandbox. For instance, when compiling A1, only A1, B1, and B2 are in that sandbox. This may sound trivial, but when you put transitivity into consideration, the size of an action input may differ in orders of magnitudes. And we did it. We gradually migrated all first-party code to Bazel in 6 months. The stats from the shadow build on CI over July showed over 50% time reduction compared to Xcode, and over 70% of the builds will finish within 10 minutes, which is way better than the original goal. You may also notice the intersection around the 25 percentile on the chart, which is because the Xcode builds are running on high-performance machines, while the hybrid one uses standard VMs. It's also worth to pointing out, as we are using the hybrid build, Cocoa pods are still built by Xcode. The build time analysis shows that it now the most time-consuming part of the whole process, and Bazel only needs a fraction of the time to build way more code. We have started to ship Bazel build QQ in August, and this migration is a huge win. In the future, we want to switch to a Bazel-first workflow so that we can gain better control over the build settings and enforce module boundaries through visibility control. Make build even faster through remote execution and smarter remote caching strategy. In long term, we want to standardize Cocoa pods as native Bazel dependencies. Thank you very much